Welcome to our introduction to networks. The term network simply refers to any number of devices connected together for the purposes of communication and data sharing. A network can be small, in the home where laptops and smartphones access a shared storage device or browse the internet, or they can be large, where multiple employees from an office in London share media files and conduct Teams calls with their colleagues in New York and Melbourne. Networks are a way of life nowadays, with everything connected together. Every time you use an app on your phone or a web browser, you're connecting to other companies' servers to retrieve whatever information it is that you're looking for. However, no matter how big or small the network, they're essentially made up of the same components, each doing a specific job. Endpoint devices such as PCs, workstations, laptops, smartphones and desk phones enable individuals to perform tasks or communicate. Servers and their associated storage appliances act as centralised functions, resources and data repositories for these individuals. Switches make physical wired connections between endpoint devices and the servers and storage, whilst access points allow wireless connections. Together, these elements form a local area network or LAN. Finally, a router connects LANs together across a city, country or continent via the internet, leading to a wide area network or WAN. Ethernet is by far the most common standard when it comes to network communication. It's been around since the early 1980s, and over this time the speeds of available Ethernet connections has vastly increased. The initial commonly available switches were capable of 10 megabits per second, whereas 1 gigabit per second is now the norm. Many businesses now also employ faster 10, 25 and 40 gigabit per second Ethernet networks. In the high-performance computing space, where complex scientific research and analysis is carried out, a rival standard to Ethernet was developed in the 1990s called InfiniBand. Although an InfiniBand network works in a similar way to an Ethernet to transfer data, InfiniBand needs less host resource to control data transmission, enabling increased throughput and reduced latency. Like Ethernet, there have been several generations of InfiniBand, starting with single data rate known as SDR, providing 2.5 gigabits per second throughput and scaling all the way to 400 gigabits per second today. Although InfiniBand dominated the HPC space for decades, Ethernet has since matched its capabilities and now progresses on a similar scale at speeds of 100, 200 and 400 gigabits per second. It's also worth mentioning that you need to match your network speeds throughout. There's little point having 10 gigabit NICs in your PCs connecting to 1 gigabit switches, as 90% of the performance will instantly be lost. Similarly, investing in a fast wired network but retaining slow wireless access will only create issues and bottlenecks for certain users. Additionally, Ethernet and InfiniBand cannot be mixed. For our journey through the network, we'll start by looking at endpoint devices. You may use a smartphone, a desktop phone, a tablet, a laptop, a desktop PC, a high-powered workstation, or maybe just a barcode scanner. However, to enable the outcome of your productivity to be shared with anyone else within or outside of your organisation, it must be connected to the network. Without a network connection, sending an email, inputting or uploading data, collaborating on a document, making a phone call, or even attending a video conference would all be impossible. With each of these devices, there must be a network interface card or NIC of some kind to allow it to connect. In the case of a larger laptop, desktop PC or workstation, the Ethernet ports or ports are usually embedded on the motherboard. In the case of smartphones, tablets and lighter laptops, the device will contain a wireless NIC that enables connectivity over radio waves with no need for cabling. Items such as barcode scanners will ultimately be wired or wirelessly connected to a PC that will most likely have a physical connection to the network. Other devices such as surveillance cameras may not be used by an individual as such, but they still act as an endpoint device as they capture footage anonymously. Similarly, these will be connected via an Ethernet cable in a network port or a wireless antennae. Servers and storage devices in the network need NICs the same as endpoint devices. However, as these elements of the network are designed for shared access and multiple resources, you'd usually want more control as to the number and types of ports. As the majority of these devices are in a rack mount format, they usually have many PCIe card slots that allow greater flexibility when it comes to network connectivity. Although the endpoint devices all connect using Ethernet, servers and storage devices, they can use either Ethernet or InfiniBand, depending on the workflows and applications that are being used. In both cases, multiple network ports are usually deployed for load balancing and failover to add efficiency and resiliency. Additionally, if servers have been virtualized, where several distinct virtual server instances run on a single physical server, many network ports are required to ensure smooth operation. These higher-end NICs seen in servers often incorporate offloading technologies, whereby the NIC assumes many of the tasks normally sent to the CPU and the system memory. This streamlining allows for higher throughput speeds coupled with reduced latency, as the data is handled by fewer internal components of the server. Both of these factors are key when dealing with very demanding workloads. It's not uncommon for servers in the network to use higher network speeds than the desktop PC and laptop users, as far more traffic is routinely sent around the network core between servers and storage devices, as automated backups and archiving functions take place. As servers usually contain the software applications that enable an organisation to function, it's also key that they can be easily managed so that admin staff don't have to be within a noisy and hot server room or data centre. And this is usually carried out by remote management via an extra network port. That allows access to the server from anywhere. This allows an administrator to diagnose, fix and power cycle a server without having to be in the same room. Servers can be configured in many ways. Similarly, storage devices are effectively servers, but with a greater emphasis on data capacity and management. You can learn much more about this by watching our dedicated Introduction to Servers and Introduction to Network Storage videos, which we've linked in the description for you. So now we've covered devices, let's now look at the elements that connect the network together, starting with switches. We've already mentioned that network switches connect everything together, and even though your phone connects over wireless technology, the access point that it connects to is linked physically by a cable to a switch. However, not all of the switches are equal in their functionality. Yes, they all direct data traffic between users, but the type of data being shared will have an impact on the type of switch best suited to the job. In a small network where the users are typically sharing email and accessing small files on the server, there's little requirement for management of the data as it's transmitted. As the number of users and devices grow, greater prioritization and segregation of the network traffic is necessary in order to ensure high quality in traffic such as video calls. There are three common types of switches: unmanaged, smart managed and fully managed, where there's a greater degree of control available to you as you climb the range. Advanced features include the ability to set priorities on either a user, device or port basis, functions which allow segregation and prioritization, and the ability to split the network into virtual LANs. Most switches will also feature a variety of port types, and for more information about these ports and network switches in general, you can check out our in-depth video, again linked for you. We mentioned that a router has the task of terminating a LAN and connecting it to the WAN in order to allow connections to other LANs. Now, although the function of a router is primarily to link to the internet, it's also fair to say that as the gatekeeper to the LAN, it also needs to make sure everything within the LAN is protected from any threats. All routers will have a basic firewall function, but businesses will need to add in a dedicated firewall router and a separate wireless controller for greater protection. And larger organisations will need an even more advanced next generation firewall alongside a separate router and wireless controllers. Similar to switches, routers and firewalls will scale in network speed and throughput. However, the greater bandwidths are put to use to analyse more data traffic and inspect it in greater depth, rather than just process it faster. As the name suggests, the next generation firewall is much more advanced, incorporating software-based intrusion prevention and detection systems known as IPS and IDS. An IDS is designed to detect a potential incident, generate an alert, but do nothing to prevent the incident from occurring. And whilst this may seem odd, it is a good solution for systems with high availability requirements, such as industrial control systems. For these systems, the most important thing is that the systems continue running and blocking suspicious and potentially malicious traffic, which may impact their operations. Notifying a human operator of the issue enables them to evaluate the situation and make an informed decision on how to respond. An IPS, on the other hand, is designed to take action to block anything that it believes to be a threat. As malware attacks become more sophisticated, this is a useful capability because it limits potential damage. An IPS is ideal for environments where any intrusion could cause significant damage. IPS systems may also contain a zero-day sandboxing function that allow them to tackle never-seen-before threats by segregating them from other traffic until they can be treated or mitigated. So wireless networking relies on a radio connection between a device and an access point that connects into a switch and the rest of the network. It's essential that the area covered by a wireless signal is strong enough to provide sufficiently fast data access for all users that need it and their workload, which may require numerous access points to ensure that the coverage is consistent and without dead spots. There are several speeds of wireless available. To get the optimum performance, the wireless NIC in your device must be of the same standard as the access point. The wireless standards are all called 802.11 with the following letter or letters to denote the speed. The first standard was 802.11b, offering speeds of up to 11 megabits per second, with the latest 802.11ac working at up to 1300 megabits per second. And it's worth noting that these speeds are all delivered in the most common 2.4 GHz frequency. 802.11a is an older standard that also provides 54 megabits per second, but in the 5 GHz frequency. Since this standard, most wireless access points are capable of using both frequencies. The reason for the invention of 5 GHz wireless was to reduce connections in the 2.4 GHz space, as this is where many other devices operate and can cause interference, such as microwaves. Access points capable of broadcasting both frequencies cannot combine the two to give greater speeds. The more users that are connected, the more management of the wireless access point is required. It's much better to keep any device that doesn't need a wireless connection on the wired part of the network. Doing so not only provides better management of traffic, but greater security and less complexity. Once again, you can get a greater understanding of this by watching our Introduction to Wireless Networking video. There are essentially two common types of network cable: copper ones that make up standard Ethernet cables and are terminated with an RJ45 connector, and fibre optic glass ones that allow faster connections with less latency. This latter type are used for faster Ethernet speeds and InfiniBand cables, terminated with a transceiver model designed to fit an SFP or QSFP type port. As we covered earlier when talking about switches, the various speeds of Ethernet and InfiniBand are delivered through either RJ45 or small form factor pluggable or SFP ports. The cables used must be capable of transmitting the speeds required. In the case of RJ45 connections, the Ethernet cables can either be Cat5 or 5E, Cat6 or 6A, Cat7 or Cat8. For the SFP type, the cables need to specifically match the type of port, either SFP+, QSFP+, QSFP28 or QSFP56, required to deliver the speeds. All RJ45 type cables are also capable of transmitting power to a device by a technology known as Power over Ethernet, or PoE. This not only reduces cable complexity, but also allows for more flexible positioning of devices. The amount of power that can be provided depends on the uprated power supplies within the switch, some being able to provide power to some ports, other lower power across more ports, and the highest spec ones higher power across every port. A PoE capable switch will be rated in one of the following 4 categories as to what consistent power it can provide. As networks grow in complexity and demand from more users, this means a higher degree of redundancy and resiliency must be deployed across the various elements to ensure there is no single point of failure that could cause bottlenecks or worse, a complete outage. Devices such as switches, servers and storage devices will often have two cables connecting them in case one fails. It also allows for a greater bandwidth and load balancing across the two connections. Whilst wireless access points can be meshed together to create better coverage and resiliency, whereas stackable switches have a dedicated stacking port that allows a daisy chain connection between up to 8 units, allowing them to be seen as a single entity, but also to fail over to each other should a failure occur that removes a whole switch from the stack. Additionally, fans and power supplies in switches, servers and storage arrays are hot swappable and redundant, making any given device less likely to fail due to a single component issue. Similarly, servers may be clustered and virtualized to prevent a component failure bringing down a critical function. And finally, it's worth mentioning that any storage drives within servers and arrays will be protected by RAID configurations and hot swap functionality. These redundancy features, all combined, provide a great degree of resiliency across the whole network. The whole network is also protected by centralised uninterruptible power supply units, or UPS, these being designed to safeguard critical process and data in the event of a total power blackout. And you've guessed it, we've also made a video about this which will tell you more about UPS. You'll find the link for this in the description, as well as other useful links and buyer's guides. So there you have it. Hopefully you've now got a good grasp of networks, their component elements and functionalities. We appreciate though that there is a lot of information to digest, so if you have any questions or feedback, please pop them in the comments section below and our IT infrastructure experts will reply to you when they can.